Okay folks, you've seen in the introductory video the different tools that we have for solving these molecular structure brain teasers. Let's have a look at an example of how we might do this. For this example, we've also got some additional information known as microanalysis data. It takes an organic molecule and it breaks down the percentage of each kind of atom in the molecule. You can see this molecule clearly has carbon, hydrogen and oxygen, and so you might actually write its molecular formula as CXHYO Z, where we have to solve the puzzle. We have to work out what X, Y and Z is, and this is really at the heart of chemical detectives and the experiment that you guys are going to be doing, is using these clues to solve the molecular formula. So let's have a look at how we might use these clues one at a time. And we start with the microanalysis data. So you can get this data for different organic molecules, and the way that you might solve a puzzle like this is by taking each of these percentages and dividing each of the percentages by the atomic mass for each atom. Okay, so we turn to our periodic table, and so for carbon we're going to do the following calculation. We're going to say 52.2 divided by 12, and I'm just going to round off the atomic mass to 12, and so we put that into our calculator, and I'll just jump across to my little calculator over here, and I calculate that value, and I'm just going to sketch that there for the time being. And I'm going to do this procedure for each of the atoms in my molecule, and hydrogen is 13%, so we say 13 divided by 1, which I can do in my head, that's equals 13. What about oxygen? Is we say it's 34.8% of the molecular mass. It has an atomic mass of about 16. I'll round that off to the nearest single digit. 34.8 divided by 16, and that equals 2.17. Okay, so what I have here is a ratio which corresponds to the empirical formula for this molecule. Now, I'm trying to solve X, Y, and Z here. But X, Y, and Z have to be integers. They can't be numbers like 4.35 and 2.175. So what I do is I take the smallest of these three numbers and I divide each of these numbers by that value. So I'm going to divide all of these numbers by the smallest, which is 2.175. And what this is going to do is it's going to give me integer values which correspond to the empirical formula. So this is obviously going to be 1. If I put these numbers into my calculator, I find that 4.35 divided by 2.175 is exactly 2. And if I take 13.0 and I divide it by this value, I actually find that that gives me a value which is really close to 6. And we've now solved the empirical formula for this molecule. So it's C2H6O. Okay, cool. Well, we've made the first step in solving the molecular structure. Now this is the empirical formula, but is it the molecular formula? Because it's not inconceivable that even though that's the empirical formula, the molecular formula could be this, where I actually have double the amount of all of these atoms. This is where we turn to our second clue, the molecular structure. And here it is here. So sorry, I'll just bring that back up on the screen for us. We think this could be the molecular structure, but well, I don't know, maybe it's this here. We turn to the mass spectrum because this gives us information about the molecular mass. And we're really just looking for one peak in this spectrum, the peak at the highest value. And it's this peak here. And if you read on the x-axis, you can see that it's coming in at a value of 46. This gives us a clue about the molecular mass. Well, we think that the molecule could be either of these two guys here. If we actually take those molecular formulas and determine what molecular mass they would be, we can see that this guy here would have a molecular mass of 46, whereas this molecule is clearly much larger. And if I add up the molecular, I should say the atomic mass of every atom in that molecule, it comes to 92. Can't be this molecule, it must be this molecule. And so you can see how we've used a combination of microanalysis data and the mass spectral data to determine the molecular mass. Okay, happy days. This is where we turn to the infrared spectrum, and these can be really complex, guys, but the important point to note here is we don't always use the entire infrared spectrum. In fact, usually we're just using it to find one or two clues. In our case, we were already up to this point here. What was it? C2H6O. Now you guys should be able to look at that molecular formula and think to yourself, okay, it's got one oxygen, so you know it might be an alcohol. It could be an ether. I don't know. Maybe it's a ketone or an aldehyde. So, you know, I'm thinking it could be something like, you know, ethanol, or maybe it's an ester. Maybe it's a molecule like this. Well, you know, so what do we do next? We look for clues in the infrared spectrum to give away the functionality. And when I look at this infrared spectrum, there's something that is screaming out to me, and it's this really broad band in this position here. It's something, it's almost the very first thing we look for in an infrared spectrum is, do you have a big broad band at around 3,200, 3,300, 400, 500, which is a clue to whether or not you've got an OH group. We'd say that this is the OH stretch band. And in this case, there's a great big band. And so it's a suggestion that you definitely have an OH group. And I'll put it to you that ethers, ketones, and aldehydes do not have OH groups. They have a carbonyl group, or this kind of connectivity in an ether. These guys have a carbonyl group, but they don't have an OH group. So I actually think that we've pretty much got our molecular structure here at this stage. I think it's an alcohol, and I think it's this molecule here. Whoops, I've got some text there. Talking about my little procedure. Let's move on to the last step, the proton NMR spectrum. It looks a little bit like this. In this case here, I have three clusters of peaks. I've got a cluster here, here, and here. In other words, I have three chemical environments. We think the molecule is ethanol. It could have been an ether. It could have been this guy here. It's got the same molecular formula of C2H6O. But we think it's ethanol. We got a clue from the infrared spectrum, so let's test it. This molecule would have how many chemical environments? 1, 2, 3. If I look at the other possibility, this ether has one chemical environment, but actually I would say that chemical environment is the same as this one. So this molecule has 3 chemical environments, this one has 1. When I look at our NMR spectrum, I clearly see 3 chemical environments. So I think it's verification that our molecule is ethanol. Okay, oops, I've got lots of text there. Let's ignore that for the time being. Look, that was a simple example of solving a chemical detective puzzle. We've got a number of examples in your lecture notes from week 3. So turn to lecture 2 of week 3 for some more examples. There's a nice section in the textbook as well if you're looking for more help. Good luck with the Chemical Detectives lab exercise.